Okay, I think we will start now. So hello everyone, welcome to today's SETS Online Great Debate within the SETS Online webinar series. I'm Teresa Nohl and I'm your chair for today's debate. First, thanks to the International Association of Sedimentologists for sponsorship of this debate and all SETS Online resources, making it possible to access a broad range of webinars, meetings and teaching library for free. So now let's start the fourth SETS Online Great Debate on the highly important but very controversial topic on the origin of carbonate mud. Is it biogenic or abiogenic? So let's first start with a short introduction of the format and some ground rules. We will first start with a quick poll to assess pre-debate opinions. Then each of our speakers will have 8 minutes to present their arguments. And we will then open the debate to you, the audience. This is an opportunity for you to put forward your case, either in support or for the biogenic origin or in support for the abiogenic origin. I would like to ask you to please try to keep this to comments and opinions. So not questions. If you would like to speak, then please use the raise hand button. And when I call you to speak, then please turn on your video and microphone. You will have then 1 minute to make your point, and then we will move on to the next person. And as with any debate, all comments must be respectful. After the audience contribution, each side is given 5 minutes to reply, comment, and sum up. And then we shall conduct the final vote and announce the results. And if anyone has any procedural question, then please use the chat function to send a message to SETS Online, and Stephen will help you out then. To clarify, the chat is turned off for any other communication. So let's get started. Today's topic is the origin of carbonate mud, the biogenic or abiogenic conundrum, and we have 4 excellent speakers lined up for you. Speaking for the biogenic origin, we have Professor John Reimer. John is Professor Emeritus of Carbonate Sedimentology and Marine Geology at the Vrije Universiteit Amsterdam. And John has an extensive record of research on carbonate platform development, paleoceanography, and sequence stratigraphy. He investigates carbonate source to sink systems, as well as petrophysical characterizations in carbonates and the transport capacity of carbonate grains. And John is joined by Dr. Laura O'Connell. Laura is lecturer at the John Logan College and is visiting researcher of Southern Illinois University. Laura's research focuses on carbonate depositional systems in temperate to cool environments. With her work, she encompasses and combines a diverse range of topics, including oceanographic aspects, sediment transport and deposition, as well as taphonomy and diagenesis. John and Laura are our speakers for the proposition of a biogenic origin of carbonate mud. And speaking for the abiogenic origin of carbonate mud, we have first Professor Paul Wright. Paul is an honorary research fellow at the National Museum of Wales in Cardiff, and he is also director of PW Carbonate Geoscience. The main focus of Paul's research is on understanding the completeness of the stratigraphic record. With his work, he has impacted many facets of the field of carbonate sedimentology. To mention but a few: taphonomic impacts on fossil abundance and diversity, forward modeling of platform geometries and their facies architecture, and paleosoil development. And Paul is joined by Professor Linda Carr. Linda is Professor of Carbonate Sedimentology and Geochemistry at the University of Tennessee in Knoxville. Linda's research focuses on integrating sedimentology, stratigraphy, geochemistry, and paleobiology in understanding the evolution of the Earth's biosphere. This includes ocean and atmospheric oxygenation and the redox structure of mesoproterozoic shallow marine systems, as well as the mineralization of microbialites and investigating potential habitable environments on Mars, to name just a few of her exciting projects. As promised, before we start, we will do a short pre-debate poll. So Stephen, please, can you activate the poll now? So please place your pre-meeting votes for today's topic and vote for either the origin of carbonate mud is biogenic or the origin of carbonate mud is abiogenic. So everybody should have now a short window, a small window popping up with the question: origin of carbonate mud is biogenic or is it abiogenic? This vote is, of course, anonymous, so please feel free to vote for either the biogenic origin and of carbonate mud or the abiogenic origin. And the results of this voting will be revealed at the end of the debate, but please vote now. We will wait a bit for everybody to vote. And just a few more seconds. We have almost all votes now. So please place your vote now. Biogenic, abiogenic, or abstain. And I think, yeah, that's it. Okay, so I think, Stephen, please close the poll. And without further ado, let's start the debate. I now call upon Laura O'Connell. Laura, you have 8 minutes to speak for the biogenic origin. The floor is yours.
Let me share my screen. All right. So I'm here today to convince you that carbonate muds are biogenic. I'm going to give some examples from several different depositional environments, marine depositional environments. And these examples, some of them you're probably familiar with, 2 of them. And then the last one is probably something you haven't seen before, hopefully, and something I've investigated recently. So I wanted to share this with you. So my first question is to try to convince you, does this grain look like a precipitated carbonate grain? So this is actually not. This is a silt-sized ascidian spicule. And ascidian is a sea squirt, an invertebrate that lives on the seafloor. And so when those organisms die, their spicules made of aragonite and have this amazing shape are then distributed on the seafloor as mud particles. So the first environment I want to share is something you've probably been familiar with before, the deep water ooze. So this is the sediment that's mostly made of single-celled planktonic organisms, coccolithophores, and foraminifera. On the left here, we see a scanning electron microscope image of a coccolithophore. And then, of course, these developed during the Cretaceous and Jurassic, these organisms. And so chalk became very abundant during this time. And here's an example of a chalk cliff along the southern coast of England. So the modern ocean is also covered in a lot of biogenic mud, and that is mostly originated by these planktonic organisms. So definitely biogenic in origin. Another environment that people are often familiar with for carbonate muds is the shallow marine realm. So this is areas kind of like back lagoon areas behind coral reefs and things like that. Shallow shelves that have these green algae that are mostly aragonitic. And these green algae, such as halimeda, shown here on the left, and penicillus on the far right, often break up into these aragonite needles that create mud-sized grains. Also, organisms that encrust on seagrasses, such as very thin coralline red algae, can also be distributed on the seafloor and break up really easily because the seagrasses die and then their substrate is no longer there. So these often create biogenic muds as well. But now we're going to go to an area that many people are not as familiar with, the cool water realm. So far we've talked about warm water and deep ocean. Now we're going to go to the cool water realm. So southern Australian coast has the largest continuous province of shallow cool water deposition. And this is a region that, of course, is adjacent to the outback, so it doesn't have a lot of terrigenous input. There's really no river coming into this embayment of Spencer Gulf, even though it kind of looks like an estuary because it's so dry. So no terrigenous input. And the sediments in this region usually look like this, right? Cool water sediments are made of gravelly and sandy, coarse-grained bryozoans, bivalves, echinoderms, grains like that. So we're familiar with that idea. And this is what they look like, right? So this is an example from Spencer Gulf. But actually many of the sediments that are found in the Gulf are caked with mud. So they do have this gravel and sand component, but a large percentage of mud as well. And so you can't just assume that cool water carbonates are coarse grained. So where did this mud come from? Based on a lack of siliciclastic input and no carbonate precipitates in this cool water environment, I hypothesized that these muds were forming within their environments of deposition, just like the larger grains were. So here's an example that shows some of the sediment depositional environments that are found in the Gulf. This is a cross section of the mouth of the Gulf. We have luxurious seagrass beds, rhodolith pavements, and then deeper water regions as well. And each of these different environments have a large amount of carbonate mud in them. So in order to kind of refine my hypothesis on what these muds are made out of, I actually made my own mud. I thought about, what is mud? Mud is just a grain size. Any grain can be broken down into mud. So I took a mortar and pestle and I did an actual experiment. I crushed up different gravel-sized particles that were easy to identify, such as rhodolith coralline algae, mussel shells, various different bivalves, bryozoans, foraminifera. And then I looked at what a mud would look like and what the chemical signature as well would be with XRD to kind of compare that with the wild muds that I found in the Gulf. So my hypothesis is that the muds are just made of broken down pieces of these organisms. There's a term called maceration, and this is broken down along planes of weakness. So there's actually pieces. I'll show you the next image. This is an example of a mussel shell. When I crushed it with a mortar and pestle, what it looks like under scanning electron microscopy, you see these calcite prisms, and this is just the structure that the mussel makes its shell out of. These structures are held together by thin organic material. So upon death, it's easy to break along these planes of weakness. Then if you look at a wild mud, I was actually able to use the chemical and morphological signatures to point count muds under the scanning electron microscope. And so this is just one example that shows those mussel shells noted with B for bivalve fragments, and then also some ascidian spicules. Ascidians, like I mentioned, are invertebrates that also release spicules upon death. So organic decay also releases some of these mud-sized particles naturally. If you look at an ascidian spicule up close though, you'll notice that it's made of this array of beautiful aragonite needles. And so these needles also break off and produce clay-sized particles in the sediments as well. In addition to ascidians, other grains also naturally break up into clay-sized particles. This is a rhodolith coralline algae, which is usually known to be a fairly robust grain, but I was able to identify a lot of these calcite, these intermediate magnesium calcite crystals that had broken off of rhodoliths and were also contributing to the muds in these environments. And so this is just a schematic of all the different ways that muds are being contributed to this cool water environment. Breakdown of rigid skeletal fragments. So this is definitely biogenic. Some planktonic organisms were identified, and also the decay of organic tissue, such as ascidians and sponges. So in conclusion, there's many different locations where you find biogenic mud. And so I think you should vote for biogenic mud at the end of this presentation. Thanks.
Thanks, Laura. I now call upon Paul Wright to speak for the abiogenic origin. Paul, please unmute yourself and start your presentation.
Can you see that? Hello?
No, please share your screen. Yes.
Okay.
Yeah, we see it.
Right. Well, I basically sit somewhere on the fence. I don't want to be one on one side or the other, but I want to draw your attention to issues which I think are as important as the origin of carbonate mud, if perhaps not more important than the origin of carbonate mud. And that is that, interesting as carbonate muds are, and whatever their origin, by virtue of their reactivity, carbonate mud plays a very critical role in early diagenesis, and that reactivity is a key element in understanding carbonate budgets and the calcium and carbon flux in the ocean. So I'm in a way trying to take the argument or take the debate and think about what it means in a broader context, rather than perhaps coming off the fence. Not what you'd expect from somebody who's supposed to be favoring the abiotic model, but this is the way I'd like to play it. As we've already seen, there are a variety of ways of providing carbonate mud. Present-day carbonate mud is clearly polygenetic. There are chemogenic muds, which are produced chemically or abiotically, things like platform top whitings, or the newer suggestions that a lot of the carbonate to the alkalinity is developing along the margins of carbonate banks and the upper slopes. There has always been a debate that whitings are purely biogenic, but we've got the arguments now particularly from Sam Perkis, about the role of oceanographic factors and how important the horse latitudes are for creating the climatic variations which can trigger whitings. But we also know, of course, as already been said, and I think John is going to develop a bit more as well, that there are biologically controlled muds. Green algae are major contributors, the breakdown of invertebrates, as Laura has pointed out, and of course the pelagic component as well. Maceration is important. We have the abrasion of ooids. Of all people have published papers on how important the breakdown of ooids is for producing mud, and microid envelopes as well, and peloids, and the origin of those, of course, is open to doubt in all cases, whether they're biogenic or not. We also have biogenically induced carbonate, microbial carbonates. We know the effect of EPS as a substrate for triggering carbonate precipitation. Photosynthesis can do it. And of course, various decay reactions like sulfate reduction can trigger the precipitation of carbonate mud. And we have this weird category I think John is also going to talk about, and that is fish excreta, where it's been estimated that between 3 to 15% of the global carbonate budget is actually produced from the intestines of bony fishes. So we have plenty of mechanisms for producing biogenic, abiogenic, and biologically induced. But when we get into deep time, which is what I'm interested in, and I think perhaps most of the listeners are in a way are interested in, and that is important as this issue of origin is. When we look in deep time, we have to consider many other factors. Has seawater chemistry changed sufficiently in terms of alkalinity and the magnesium-calcium ratio to have affected the precipitates that are abiotic? And temperature, of course, has also played a role. This is going back to Sandberg's work now 30, 40 years ago, and also the newer ideas by Balthasar and Cusack looking at the role of temperature in controlling which polymorphs are produced. If we look at biotic mud makers, as Laura's already mentioned, we have calcareous green algae. Were they as common as they are today in the past? I don't think so. Did they produce calcite, not aragonite, or even not calcify at all? The red passionellids have a very complicated history of whether they calcify or not. And this may relate to oceanic alkalinity or, again, magnesium-calcium ratio. And microbial carbonates, Riding and Liang have pointed out that the formation and preservation of microbial carbonates through time seems to directly link to the saturation state. So regardless of what's making them, other things have been taking an important role as well. But at the end of the day, what we end up with in deep time, of course, is a mixture of micrite and microspar. We may start off biotic or abiotic or whatever with mixtures of aragonite and calcite, where that red star is, but we end up with LNC. If we look at just one compilation, this is of a subset of carbonate muds in deep time by Hasiuk and co-workers. They've looked at these carbonate micritic microsporitic grains that are associated with microporosity, and we see from the oxygen isotopes a very, very wide range. Some of them certainly fall within the range of what we'd expect from precipitates from modern seawater. So these are strongly telling us there's a contemporary seawater influence. But also, as we go down this isotope line, we're seeing that there's a diagenetic overprint. Really, knowing that these muds are altered is not surprising, is it? It's what we've been talking about for generations when we look at diagenesis. So it's not a surprise. It's not a surprise, especially because, as we all know, modern day carbonate muds, which are dominated by aragonite and high-mark calcite, are highly reactive. We've known now for at least 30 years that they alter very rapidly, often via complete dissolution in very shallow marine pore waters. I'm talking about centimeters to meters here. And that these alteration processes where we dissolve or replace some of these unstable polymorphs are actually microbially mediated. So they're ultimately abiotically modified. One of the most detailed reviews, of course, is by Birdie, so I draw your attention to that. And Sun and Turchin have made the point that what we're dealing with is what they call the carbon and calcium reactor. Some estimates have suggested that 20 to 50% of the carbonate is lost syndepositionally in modern environments in very shallow water. And much of that would have been mud. And one of the contributions most recently on this is by Gaiman et al. In 2022. But carbonate muds are more complicated. So let me make matters worse in terms of what we're dealing with in deep time. And that is that when we see lithified carbonate mud in deep time, are we sure that it's in situ in the first place? Or has it been moved or translocated? Or was it ever mud? Maybe it was never mud in the first place. In fact, some carbonate mud rocks are purely diagenetic, precipitated interstitially as cement. They look like depositional mud, but they were never, or in some cases, were never depositional mud. And yet the majority of these, and here I'm talking about diagenetic bedding, have contemporary marine isotopic signatures. So when we, for diagenetic bedding, which also relates to nodular bedding, numerous studies by workers such as Axel Municher, Hildegard Westphal, and more recently by Teresa Knoll, have made a very strong case that a lot of the mud we're seeing in this diagenetic bedding is where we have basically remobilized dispersed aragonite and low-mag and high-mag calcite, predominantly aragonite, disperse that material within the sediment. And they're easiest to see when we're looking at these limestones in limestone marl alternations, because we have a siliciclastic host rock, a mud, siliciclastic mud, and the carbonate really stands out. This is where they make these dramatic LMA outcrops, limestone marl alternations, or bipartite bedding. But what's happened is we've simply reorganized the carbonate in there to produce receptor and donor units. And much of that carbonate, it's been shown in studies, has been derived from the dissolution of aragonite. Much of it would have been aragonite mud, but what we see now has been highly altered. But what if it was never mud? Another possibility is here that in some LMA successions, there is fossil evidence for the huge loss of former aragonitic fauna. In other words, that the aragonite we're seeing producing carbonate mud in deep time, perhaps the majority of carbonate mud in deep time, a lot of that aragonite was not produced from mud itself, but from shells. There's a significant textural difference, if you like. We know, we have evidence from, again, this is an example, I've just shown you a picture of it. It's from the Jurassic of South Wales. We have evidence that the faunas in these limestones now, these LMAs, limestone marl alternations, the faunas we see today are all calcitic or bimineralic. But where we have a life assemblage preserved in a skeletal Lagerstätten, 84% of the original fauna was aragonite. In other words, there is a catastrophic loss of skeletal aragonite, not mud-grade aragonite, but skeletal aragonite, which could be sourcing some of this. So it's complicated. When was mud mud? I'd like to paraphrase George Orwell in Animal Farm. All ancient carbonate muds are diagenetic, but some really are more diagenetic than others, and they were possibly never mud in the first place. In summary then, whatever the origin and composition of carbonate muds may have been in deep time, shallow tropical muds today clearly go through a microbially mediated reactor, which we're seeing in this part of this plot, from the Hasyuk data set, and that later on there's some modification. So at the very best, by the time this stuff ends up in the rock record, it's been affected by microbial mediation. So is it biotic then? and also probably in deeper burial by more abiotic processes. One of the debates that's going on at the moment is whether this zone, this red zone here, where we see a signal from contemporary marine seawaters, is that zone, is it meters thick or perhaps 100 meters thick, as there have been some suggestions in the literature recently. Now, what interests me is the big picture. This subsea floor carbonate, calcium and carbonate system, or a reactor, as Sun and Turchin call it, they argue that this is a non-negative part of both the global biochemical calcium and carbon signal. And in fact, there are some studies which have argued that as much as 25% of the dissolved inorganic carbonate we see in the geological, in modern systems, such as in the Adriatic, has actually come from shell dissolution, from aragonite in particular. So carbonate mud, of whatever origin, and I'm quite happy to have it polygenetic, is so modified in deep time that we really do need perhaps to be thinking about how important these early reactions are in terms of global sediment budgets as well as global carbon budgets.
Thanks a lot, Paul. With this, I would like to give the mic to the next speaker, which is John Reimer. Please share your screen now. John, we cannot hear you yet. Could you please turn on your mic?
Sorry. Okay. All right. As you can see in the background, I like the biota. I like farms. So I like also what cows produce, right? They produce a lot of mud. In carbonates, it's different. I listed 5 types of stuff you can make, how mud can be formed in carbonate environments, like fish chewing on corals. They can make a lot of mud. Some nice studies by Perry et al. On that one. Going back in time, green algae, when they fall apart, you produce a lot of small little needles, also a lot of mud. Then white things, what I highlighted in red, that's my main thing I'm going to talk about. But also the chemical precipitation, the study by Wright in sedimentology, is a possibility to produce mud, but also transport and abrasion. I'm going to make a high big case for whitings, right? These big clouds, white clouds in the water column on shallow water carbonate platforms, but also on lakes. It doesn't do it. Also in lakes, okay. The first study I'm going to highlight is a study on the Fayetteville Green Lake in New York, USA. That's a study by Stanton et al. That recently appeared in Geological, and that also highlighted some earlier studies on the same lake by Thompson et al. In 1997. And what they clearly showed is that cyanobacteria and diatoms, together with surface warming in summer and spring months, you produce a kind of engine of parts where crystals can start forming, right? Because the cyanobacteria and diatoms, they produce microbial cells and EPS, and in interaction with the water, you produce small little blobs, carbonates. They clearly demonstrated for this lake that if it would be entirely abiotic, then there would be a decrease in the pH and the CO2 budget of the entire lake. That's one thing they did not observe for the Fayetteville Green Lake. What they really saw, there was a biologically induced mechanism in which these EPS, microbial cells, diatoms, they kind of enhanced the environment on which carbonates were being formed. On the lower side, you see one of these cyanobacteria. In the middle, several types of diatoms, centric and pennate, and on the right-hand side, it's clearly shown that the diatoms, they expel EPS, and on this EPS, small little blobs of carbonate can be formed. So it's the biota that starts, and then abiotic takes over, and when the biota just disappears, you end up with nice blobs of carbonate, which you think are abiotic. So in lakes, biotic, definitely. Then we go to the Bahamas. When you look here, there's a study by Perkins et al. Just recently showed up in JSR, in which he showed that waters entering the Great Bahama Bank, shown on the upper left side, in the winter times, they produce more of these whitish clouds of whitings. And he also demonstrated that it clearly was the interplay of hydrodynamics, temperature differences, and water chemistry, and the mix of off-platform waters that entered the entire realm, on which these whiting clouds, these clouds of fine little needles, could be formed. But he also demonstrated that you need a certain size of platform to form these clouds. Of course, you think, okay, I can produce that in an abiotic way, but when you have seasonal variations, and these seasonal variations on the platform are directly transferred into production of needles and transport of needles, and they show a certain cyclicity, I think there must be some biota involved. We're going to look at a core on the western side of Great Bahama Bank, 38 meters, was analyzed for mineralogy, so there's definitely a lot of aragonite in there, some high magnesium calcite, some low magnesium calcite, and it was dated with a lot of C14 dates, so there's a clear, I should say, it's really engulfed in time. So I know which time certain mineralogy was being deposited. When I analyze these cycles of aragonite, next slide, I can do that for measuring XRD and doing the aragonite, but also can measure the color and then look at the whiteness of the color and compare that to the aragonite, and you see that I have a clear, nice record over 7,000 years with a 1-year resolution at the base, a 5-year resolution at the top, which clearly shows kind of variations in production of needles. These are definitely needles in the core. Here at 1 meter, when you go to 10,000 magnification, you see these nice stubby needles. When you go to about 33 meters, once again, stubby needles. And when you compare the shape of these needles with the whiting needles, they're more or less the same. So these whitings are produced 38 meters, 7,000 years. All the time, these whitings show up and go away. And they do that in a cyclic way. Here's a spectrum of the aragonite record. And here are some possible origins or causes and effects. Where you go from multimillennial scale to 60 years and even lower, you can even go to 20 years. You see that climate and atmospheric changes is directly transferred into changes in the water column, with seasonal variations in production and transport of needles. And how do I produce these whitings, these needles? I just need a biota. Recent studies show that it's really phytoplankton, diatoms, and microbial cells. Lloyd et al. Showed that there was seasonal variations and slight variation in pH and phytoplankton blooms. They produce those needles. The same was shown by Yao et al. Just recently, seasonal variations in production of needles, phytoplankton, that allows these crystals to be formed, these needles to be formed. So I think my discussion and conclusion is that you have seasonal cycles of blooms of phytoplankton and diatoms, also on the Bahamas, that produce EPS, and that's the starting point for these needles to form. And later on, when all my EPS dissolves, you end up with nice muds, needles that are of originally biotic origin. So just to summarize, I think that whitings are biotic or biogenic, however you will call it. They show a seasonal appearance, not only on the Bahamas, but also in the lakes. So my argument is you can produce a hell of mud, 38 meters on a Holocene wedge, of pure needles that are started with a biotic origin and ended up abiotic as we see it now in the wedge. And to come back to the talk of Paul, 38 meters of mud, but no diagenesis. So how come? Thank you.
Thanks a lot, John, for making this argument. We will now proceed to our last speaker, to Linda Carr, to second the abiogenic origin. Please, Linda, the stage is yours. Unmute yourself and share your screen.
Okay, well, I have a lot to follow up here, but I'm going to, I think, take Paul's lead and sort of try to change the question. You know, for full disclosure, I sit completely on the fence when asked to participate in this. I said I thought it would be fun. They said biogenic or abiogenic, and I said wherever you put me. And because I don't really think of muds and carbonate muds as purely biogenic or purely abiogenic. And so for full disclosure, you know, I'd like to turn the whole question around. I'd like to ask the question, to what extent does blank play a role in the formation of carbonate mud? You know, to what extent does the breakdown of biogenic skeletal elements, to what extent does the templating and nucleation on organic molecules make a difference? To what extent does local modification of seawaters make a difference? To what extent do global seawater changes and chemistry make an effect in the formation of carbonate mud? And so, you know, to put up the same triangle that Paul put up, what I particularly want to note is if we think about an abiogenic formation or an abiotic formation, we're typically thinking simply of chemical carbonate formation. And on our lower two corners of our ternary diagram, we have biologically controlled. So these are skeletal elements that are clearly templated by enzymes that make that. So I put up a beautiful, this is Cretaceous, a Cretaceous echinoderm. My husband's an echinoderm worker. So we can see the extent to which biological control can play a role in the morphology of carbonate. And on the other side, I have the biologically induced, which is largely what John was just talking about. So here I have a little cartoon from Rob Riding of carbon concentration mechanisms that result in localized changes in the pH and alkalinity outside of a cell. They provide OH to the outside of the cell, make things a little bit more alkaline, and you can get precipitation either within a sheath if you have a nice EPS sheath, or potentially as biogenic whiting crystals. Now, the problem with this ternary diagram, which is, it's not really a problem. The great thing about this ternary diagram is it really does spell out what the problem is. A difference between a purely abiotic carbonate and a biologically controlled carbonate is typically really easily distinguished. The difference between an abiotic carbonate and a biologically induced carbonate is not so easily distinguished. And I am not certain, given that I also work in deep time, but when I say deep time, I mean the middle Proterozoic. So when I'm, you know, looking back into the Precambrian, you know, if we cannot determine that something had an effect of a biological metabolism, can we actually say that that is a biotic, you know, can we say that biologically induced precipitation is in fact biological? And I would argue that no, it is dominantly abiotic, and the biology just happens to be changing the local environment. To give an illustration of this, I have again, this cartoon of Rob Riding's suggesting carbon concentration mechanisms. These are well-known in photosynthetic microbes. But we again have to ask, how well can we distinguish abiotic versus biologically induced mineralization? On the right-hand side of the slide, we actually see what happens when you put a brittle star in bleach. And in fact, about from a single brittle star, about 90% of the number of plates are in fact mud size. That makes up a relatively small volume, but it is a large number of mud size material coming from a single brittle star. And here we have a larger component. This is a brittle star vertebra or an arm piece that shows all of the stereome and the classic biologic control of the morphology of this carbonate. And so I think we can clearly say that something like a carbon concentration mechanism, some biological induction, has very little to do with the formation of a carbonate grain from a brittle star. However, if we take something like a calcified algae, if we take something like a halimeda, which gives us these randomly oriented aragonitic lathes, can we actually say that that is biologically controlled? Or are, in fact, a lot of the calcified green algae that we see today actually just an effect of carbon concentration mechanisms, and we're getting what is essentially a biologic carbonate formation within a biological structure? We also have to consider that carbonate muds occur through geologic time. This from Canteen et al. Clearly skeletal or enzymatically produced carbonate has only been available as a source for carbonate muds in the last 540 million years. And we need to think more broadly about carbonate muds if we're going to do justice to the whole stratigraphic column. If we particularly look at the uppermost left graph here, we're looking at this yellow color. And we actually see the yellow color from the late Archean through the Paleoproterozoic, through the Middle Proterozoic, through the Neoproterozoic, that we don't see a huge amount of difference in the volume of carbonate mud, which means that the vast majority of the carbonate mud that we've had in the geologic record has nothing to do with the breakdown of skeletal elements. This is part of the reason I really like the Gaiman et al. Paper that came out this past year, and I wrote a little sort of news and views on it, because what they did was a very careful study of Bahama Banks muds. They identified the skeletal components of the muds, used isotopes and trace elements and probabilistic mixing models to say whether or not you could create the mud from those individual skeletal elements, and showed, well, you could create the trace elements that we see of the mud, but you can't create the isotopes. You couldn't actually get all of those. And so they were able to recognize an unknown M member and then use clumped isotopes to look at temperature of where these things were forming and say, hey, it doesn't even look like that the vast majority of the carbonate mud is actually forming on the bank, on the bank top where it is warmer, that is likely forming in the deeper waters. And so they actually hypothesized it in this part of one of their figures, is that what we're seeing is higher alkalinity, deeper waters, and this alkalinity largely in their story being driven by transport of alkalinity from the Mediterranean, rising along the shelf, warming, degassing, increasing carbonate saturation. And so they hypothesized alkalinity as a key parameter, or in my words, alkalinity is the secret ingredient. And I think that this alkalinity is incredibly important because we need to remember that what alkalinity is, which is described in this slide, and that alkalinity is dominated by changes in the carbonate alkalinity. And so changes in marine alkalinity have a large effect on the carbonate system. Why do I like alkalinity as a very important driver? It varies regionally in the oceans. Alkalinity varies locally, even within benthic microbial mats. So I have a picture right here of a microbial mat. This is a tufted microbial mat from 1.2 billion-year-old rocks in northern Baffin Island. Each of these tufts is about a centimeter. The largest ones are almost 2 centimeters. And then they're actually draped by they are themselves composed of carbonate mud, and then they are draped by this white carbonate mud. But what we see is that alkalinity, if we actually look at our set of microbial reactions, which we tend to have in nature, and we likely have had in nature for the vast majority of Earth's history, that we actually see that several of these have very large effects on alkalinity, and as a reflection of that, an effect on carbonate saturation. This is biological induction. This is biology just being biology, not saying what the carbonate is going to look like, but changing environments in which carbonate can form abiotically. I also like increased alkalinity as a secret ingredient because it actually allows us to look at the depth of geologic time. We don't necessarily have to just look at today's system. If we just take this as an example of a dominantly anoxic ferruginous ocean from Schott et al. 2019, here looking at the microbial iron cycle, we can actually start to consider what is actually going to happen to the alkalinity of marine systems when we have a persistent anoxic ocean. Because the fact is, at this point, our conservative elements are not just sodium, magnesium, calcium, and potassium, but in a persistent anoxic water body, we will also add in iron and manganese as part of our alkalinity. That is going to change our carbonate alkalinity as well. Other issues that we still need to deal with, and just finishing up here, is we need to be able to nucleate it. We've all seen that it takes a big energy gain, so people often think of a very high supersaturation in order to nucleate carbonates. But there are different ways of doing this. We can either have some sort of a templating. That templating can be organic molecules. That there is organic matter there doesn't mean it's actually playing any sort of an active role. But we also have non-classical nucleation theory that suggests the much greater likelihood of pre-nucleation clusters. So these are often unstable to metastable hydrated carbonate that can actually form within a water column fairly easily. So if we start to think about this and think of all geologic time, for the last slide, can we actually learn anything from the Precambrian? So I have two sets of pictures here, two of microbial mats that then have these beautiful white drapes. The microbial mats themselves are carbonate mud, as is the white drape, which is allochthonous carbonate mud that is overlying them. When we actually look in pre-skeletal time, we still see a hell of a lot of mud. The vast majority of this, though, does appear to be precipitated in situ within microbial mats. And so whether or not you want to say that the precipitation there means that it's biotic because of a happenstance conversion in locality of microbial mats and the carbonate crystals, that may be. We also have things like molar tooth microspar, which is also a carbonate mud that forms in the water column and in the shallowest subsurface in cracks and voids that are typically attached to the overlying water column. These don't seem to have any very clear interaction with microbes because they form in voids. And so when I put all of this together, what I say is, we can't spit without hitting biology on the Earth at pretty much any time in the Earth's past, but that doesn't mean that the carbonate that is forming is biotic. Thank you.
Thanks a lot, Linda. Thanks to all of our speakers for their excellent arguments. I will now open the debate to the floor, to everybody. And just as a reminder, if anybody would like to speak, then please use the raise hand button. And once I've asked you to turn on your video and microphone, please start to make your case. And you will have around 1 minute to make your points, and then we shall move to the next person. And please keep all comments respectful and in line with the rules of SETS Online. And any questions can be answered by the speakers during their summation. So we are waiting for the first audience comment. Please raise your hand if you would like to share a thought or a comment. So while we are waiting, everybody's welcome to share their thoughts. Don't be shy. We'll wait a few more moments. This was, of course, a lot to digest. A lot of great arguments. Oh, we have a comment by Natasha Morris. Natasha, please unmute yourself and also turn on your camera. Are you able to? Yeah. Okay. Hello. Natasha, can you turn on your microphone and your camera?
Can you guys hear me now?
Yes. Perfect.
Okay, I can't seem to turn my video on. Sorry about that. Yeah, my background's a bit different. I'm not, a lot of this was a bit over my head, but oh, it was fascinating. I was really interested, Linda, in your alkalinity, just because I've been looking a lot at the sulfur, the role of sulfur, and I'm just wondering, I know in that one diagram you showed the sulfate sort of and how it interacts, but could you guys all kind of speak to maybe on a more higher level the role of sulfur in the abiogenic versus biogenic mud debate? Or anyone just have any comments about that?
Okay, so we have a question for the later argument. Please keep that in mind. We will answer that, or the participants will answer that later on the sulfur, on the influence of sulfur. Okay, we have another comment by Mohammed Hashim. Hi, Mohammed. Good to see you. Please unmute yourself.
Hi, Teresa. Good to see you too. Hi, everyone. Yeah, this is really interesting. I learned a lot today. I just wanted to bring to the attention of everyone the idea of a potential bias in terms of the environment that we look at, right? So a prime example of this is the Bahamas, right? So like we have seen the Bahamas a lot today in different presentations. It's a fascinating place. I study the Bahamas as well. It's great for carbonates and carbon diagenesis, but I wonder if the way we think about mud and carbonates in general is influenced by where we go and what we study. So I think an example here is, I think a better case or a clearer case can be made for inorganic origin for whiting in other places, like the Persian/Arabian Gulf, for example, where Friedman showed that it seems like it's actually inorganic based, I think, on trace element and isotopes. I just wanted to bring this idea. No question here.
Thanks a lot, Mohammed, for this comment. That is a great point. We have another comment by Patrick Hensel. Patrick, please unmute yourself and turn on the camera. Hi.
Can everybody hear me, see me?
Yep.
Okay, so I have only one opinion comment. So I think that for creating the carbonate mud, it starts with the biogenic factors, and then the abiogenic ones will be the consequence. So I think there's a strong interfingering between both, but I think it starts with the biogenic side. So that's my opinion.
Thanks a lot, Patrick, for your thought on that. And we will continue with Mariano. Mariano, please.
Thank you very much, Teresa. So I have a kind of a question for John. Do you think, John, that this cyclicity that you observe in whitings could be the potential driver for the marl limestone alternations that we see in the geological record? Thanks.
Do you want me to answer now, or?
Please answer to that later.
Right.
Maybe you can join Laura briefly in the discussion. Have we any further thoughts? Please bring them forward now. We wait a few more seconds. So I think, yeah, we have one more person. Jim Henry, please unmute yourself. Hello.
Oh, hi there. Sorry. Yeah, I mean, the answer seems to be obviously a bit of both and quite a lot of the in-between in terms of the biologically induced precipitation. But the thing that struck me is I was taught carbonate sedimentology a long time ago, and I was taught that carbonate mud equals micrite equals less than 4 microns in size. And very many of the examples I've seen presented to us so far are quite a lot bigger than 4 microns in size. So I would just be interested in the further debate to hear what the panelists have to say about that. Thank you.
Thank you. Yeah, that's an interesting point for both sides to comment on. Do we have any further comments? Please don't be shy. Just share your thoughts with us. We'll wait a couple of seconds more, but I guess everybody who wanted to comment has. So we shall now move forward to and end the floor discussion. Thanks everybody for your thoughts and insights, and I will now call upon Laura, who has now 5 minutes to present the rebuttal and to defend the biogenetic origin. Please, Laura, go ahead. John, you're welcome to join.
I think John should join also, if that's okay.
Okay.
But yeah, I think that it's been proven by this debate that it's biogenic in origin. So at least a combination. But I was intrigued by Linda's discussion of kind of whether the biogenic origin is on purpose or not, is kind of how I interpreted it. But yeah, so we have a lot of examples of biogenic origin of muds, including whitings, which I traditionally learned as abiogenic, and wasn't that long ago. So I think the tables are turning towards more biogenic origin. And regarding the size that was discussed just recently, I was kind of going with silt and clay sized particles. So the clay size is less than 5 microns, so similar to the micrite that was just discussed. And a lot of the grains, at least that I've encountered in different regions, are just broken down further into the smaller sizes. So still skeletal in origin based on the chemistry of those and the morphology of those grains. So I think if you don't mind, John, also giving some input.
Yeah, I think the grain size is already solved by the size of the aragonite needles. That's way below mud size. And to come back to the limestone mall alternations, we actually took that core on the slope to evaluate if 38 meters would be enough to make limestone mall alternations. And the 38 meters of mud were just pure mud, so no diagenetic start already. So perhaps it's deeper. I discussed it about 3 weeks ago with Axel Munike in Erlangen. I think we agree to disagree on that one. I think it's, if you have 38 meters of mud and you still don't see any diagenetic modifications, I find it difficult to believe that when you go deeper, things will change. But okay, that's something we need to find out in the future. Other questions? I think it's a kind of interfingering, like was discussed as well, that you need some biogenetic thing to change the environment on which a crystal can precipitate. So, and then the biogenic thing moves away and you're left with the crystal. So it's the same when you go to corals, right? You need a kind of matrix on which you can form the ACC, the carbonates. So, and as for the Arabian Persian Gulf, in the same study by Stanton et al., they showed, or they discussed at least, that there's an organic start as well. So I think it will be the mix, right? You start with something biotic and you end up with something abiotic. And at the end, especially we go back to the proterozoic, you can't prove that there was something biotic anymore. So that's my final point. So I'll vote biotic. That's it.
Laura, do you have any final comment, or does the biogenic side conclude?
I think
there?
that was good. Thank you.
Perfect. Okay.
Thanks, John.
Thanks a lot.
Thank you,
I would like to ask Linda to make the concluding comments for the abiogenic side. Please go ahead.
Okay, and I will again offer to Paul to speak at the very end if he so chooses. So I'm going to get a little bit fussy right now about terminology. And I want to first say to Jim Hendry that the slide on micrite, microspar, pseudospar was actually taken out of my presentation. If we actually look at a modern definition of mud, which is an indeterminate mixture of clay and silt-sized particles, then we can go up to 63 microns. And so that takes us out of necessarily the role of micrite into larger things, which makes this mixture much more possible. And so I think as a closing statement for the abiotic side is that I think it's the wrong question because I think it depends on when and where you are. I think it's really an extent to which. And I personally, and I will admit straight up here up front, that the last decade I've spent most of my career a little bit further from carbonates and on Mars, and looking at habitability in Mars, looking at minerals on Mars, looking at even carbonate on Mars and stuff like this. And so I get really picky about the use and how we actually think of something like biological induction. Because one of the difficulties with that term is that it is not translatable to any place else, any other planet, because Earth is the only planet on which we know that life exists. And we also know that we can't do anything on Earth without hitting a microbe. And so I consider, because most of the biologically induced, or what we infer to be in biologically induced carbonate formation, is in fact that it is an inference that the actual formation of the carbonate most often whether it's within the sheath of EPS or as whiting muds, is an abiotic process that is potentially driven by microbial actions or microbial templating. The thing is, you could have organic templating that's not microbial. On Mars, we think a lot about organic molecules that are abiotic organic molecules. They're abiotic in origin. And we have a lot of trouble if we want to insist that something that we cannot physically either before or after diagenesis recognize as having a morphology that is determined by the biology, that is deterministic of that biology. If we can't recognize that, I think we have a hard time saying that that is biologic. We can infer, we can interpret that it may be biologically induced, but that precipitation is fundamentally abiotic, which is why I'm happy falling and arguing for an abiotic origin. In general, I think that Jim Hendry had it right. It's a bit of both and quite a bit in between. Okay, Natasha, you asked about the role of sulfur and sulfate. Generally, sulfate in a water column acts as inhibitory to carbonate precipitation. This may not be a problem actually for most of Earth's history, because for most of the Proterozoic and the lower Paleozoic, we had probably less than half the amount of sulfate that we have in the ocean today. And by the time you hit the middle Proterozoic, you're probably talking 1 or 2% of the sulfate that we have today, because we simply didn't have the amount of oxygen in our biosphere. The other question that Mohammed asked about whether the potential bias, I mean, I think that we are exactly right, and this is one of the arguments that I'm making, is that we are biased not only to the delight of whitings, which are so exciting and so interesting and so enigmatic that that's what we want to study and look at, but we're also biased, and you've seen the bias here, between people that are looking more at the modern and people that look at deep time where diagenesis has taken hold. And with me, we're also looking at a bias of what we think as being terrestrial geologists versus trying to think of a broader system that might include other planets as well. We have a lot of biases, and it's the most important thing in science that we recognize those. Paul, you have anything to say at the end?
When I teach carbonate photography, the first thing I say is that sedimentologists are very bad carbonate sedimentologists because they use the word micrite to mean mud. But micrite, of course, is a component of carbonate mud. And mud is a grain size distinction. Micrite is just a term used for a minor component of many carbonate muds. The thing that's bothering me is the use of, and this has come up about bias. People are biased to what environments they've worked on, the Bahamas or somewhere else, or they're biased to which parts of the geological column, Precambrian, deep time, subrecent, Holocene, whatever, they're biased in that way. But to me, the worrying thing is that bias, although it's a natural human thing to do, can be very damaging. If at the end of this, the biotic vote wins, then we failed as scientists, haven't we? I think there can be little doubt that muds are polygenetic. It would be ridiculous to claim there are no physiochemically precipitated carbonate muds anywhere. So we should accept this polygeneity and investigate muds to determine that. But the problem is that once people walk away from a session like this and say, well, that's proven it, muds are biotic, then believe me, that creates a mess. Whether we like it or not, it creates a mess. And I spent a decade trying to persuade people that the pre-salt carbonates in the South Atlantic were not biotic, because somebody at the beginning of those studies said it's all biotic without any evidence. So please don't vote, accept that there's polygeneity, except that that's what science is about, is keeping, an open mind about things. It would be ridiculous to claim that there is no physiochemical processes on this planet today that will precipitate fine-grained carbonate. That's a sort of intellectual fascism to claim that. But we need to investigate these carbonates more carefully to identify them.
Okay, thanks, Paul. I would still like to encourage everybody to take part in the poll. We also have the button to neither agree or disagree or choose one, so you can also abstain. I would like everybody to still participate in the poll. But thanks for making the arguments, and everybody for wrapping this up, and we shall now move on to the final vote. So Stephen, please start the vote, and just as a reminder, this is as the first one, anonymous, and we will compare the results then from before the arguments were presented and afterwards. So please do vote now, and yeah, you have now the chance to vote either for the biogenic origin or the abiogenic origin, or if you want to follow the argument that neither of them, or actually it's a combination, then please click on abstain. So we're waiting a few more seconds. Everybody should see the small window where you can vote. Okay, so the poll is closed now, and just before we have a few more announcements. Next month, we will be back with our regular webinar series with Cynthia Nava-Fernandez from the Ruhr University Bochum on El Niño Southern Oscillation imprints recorded in Southwest and Central Pacific caves. And during the meantime, please check out our website and YouTube channel for over 3 years of SETS Online webinar recordings. And I think we have the results now. So for comparison, initially we had 59% for biogenic origin. We had only 16% for abiogenic origin and 25% abstain. The final votes are 35% for biogenic origin, 19% for abiogenic origin, and 46% for abstain. So I hope with that result, also Paul is happy that the majority is for neither strictly biogenic or strictly abiogenic origin. And with this, both sides actually defended their argument greatly. And we've heard a lot of excellent arguments for both of the biogenetic and the abiogenic origin, and how the discussion actually gets more complicated the further we go back in time and by adding diagenesis. So we've heard a lot of food for thought today, and I definitely enjoyed this great debate a lot. And with this, I would like to wrap up and thank again all of our speakers for the time and efforts. And also thanks to the IAS for sponsoring all of our activities. And also thanks to the Geological Society, which has recently awarded SETS Online the H.R. Worth Medal on the for contributions to the geological outreach. And I would also like to thank the SETS Online team, in particular Marianne and Brian, for setting up the great debate, and thanks a lot to all our helpers. And we shall be bringing you future SETS Online great debates in near future, and we look forward to seeing you at next month's SETS Online webinar. And with this, I would like to end the great debate. Thanks also to the audience for listening today and taking part. Thanks again, and bye.